So back in the nonlinear optics lab again, and this time we have our friend here, beta barium borate, BBO, generating SPDC photons using a 405 nanometer pump source, and this crystal then generates twin pairs of 8 to 10 nanometer photons, which are then fed into this multi-mode fiber. And a new addition to this setup, this big long twisting fiber, is this thing. And believe it or not, this is a laser, a neodymium YAG laser that's been basically salvaged from a laser tattoo removal machine. And what I'm doing with this laser is I'm actually using the neodymium YAG crystal to act basically as a cavity to store the 810 nanometer polarization entangled photons. And what this does is, when it's actually powered on, it acts almost like a kind of an echo chamber. So there is a very famous actually effect called the photon echo effect, in which if you actually pump a rare earth ion crystal, you can actually, in a way, you can actually inject a second, if you like, in this case, pair of photons, and you can sort of have them ride, if you like, the wave of the primary pump photon, which in this case is provided actually by a broadband light source, a xenon flash lamp, powered by a stroboscope, actually, a strobe light source. And what this does is it effectively allows one to actually store entangled photons, at least in principle, using the metastable excitation levels of the neodymium 3+ ions that are embedded in this, if I zoom in on it there, neodymium YAG crystal. Now, to kind of borrow an analogy, it's a bit like, if you like, the concept of an echo in a cave, sort of acting sort of as a memory, if you like, whenever you shout into a cave, or I don't know, tap a rock in a cave, or even fire a gun inside of a cave. The echo reverberates, of course, inside the cave, and if you like, rides along the cavity or the different cavities within the cave. Maybe there's several layers of cavities within the structure. And what this does is, of course, if you ever shout your name into a cave or a hollow cavity, you get it actually reverberating enough times off the walls, and it effectively acts as a sort of a natural memory or a recoverable memory. And of course, in the case of a cave with sound waves, the echo will be broadened, but the same thing happens actually with the photon echo effect as well. And the larger the cavity, of course, the more probability that there is that the echo will be maintained over the period of, again, in this case, a few fractions of a second. So, among other things, it acts as a sort of a memory, but also the equivalent of, let's say, several kilometers worth of fiber optics that would otherwise have to be laid down and made polarization maintaining, but in this case can be actually nicely kind of secured within basically a 10 centimeter or so device. Again, salvaged from a laser tattoo removal machine. So what I'm doing with this, along with my other nonlinear optics kit, I'm doing polarimetry using polarization controllers, which set a particular basis, either a random or a quantum measurement basis, such as the Bell basis, and so on. But the key kind of feature of this setup, which makes it unique, at least to me, is that I'm actually doing polarimetry. I'm projecting the entangled states onto the Poincare sphere. Each polarimeter has its own polarization ellipse and Poincare sphere. They can be shared in this particular plot. And what this setup does is also measure the Stokes vectors, allowing one to construct a density matrix and a Wigner function, say, but it also records the power. So the power is very low here. And what this setup also does is, when I switch it on, and you'll begin to see it actually in action, because the setup is actually meant to be contained in a device, but in this case it lets you actually see the flash like a disco almost. So this is the crystal actually lasing. I've actually showed this crystal, this setup actually many times on my YouTube channel because I've used it for, among other things, just general tests of basically lasing technology, but I've even used it for solar powered lasing, and I can adjust the rep rate and have a pulse. And what it does here is it actually shows the amount, if the computer hasn't gone to sleep yet, the amount of power. Yes, so a little bit of a boost of power. So it not only acts as a memory, but it acts as sort of an amplifier of sorts as well, which makes sense of the particular band that's entangled to 810 nanometers. So neodymium YAG, the crystal, actually, when it's pumped with a broadband source or a diode source, say 8 to 10 nanometers, it actually turns the wavelength into 1064 nanometers by, if you like, classical optics. But with quantum optics and the photon echo effect, you can actually allow, it allows one to, if you like, neglect the normal conversion procedure and actually, if you like, literally surf, if you like, the wave of the input echo pulse. So quantum echo, photon echo memory is being examined for potential use in for quantum memories in general, and there's actually a ton of research published on this, such as this quantum light storage using rare earth ion doped solids. And neodymium YIVO is a good one, and neodymium YAG is the one I'm using at the moment, but they basically use both the 3+ ion state of neodymium to store the light memory. So there's a ton of research published in this, and the attractive thing is it can be done at room temperature. It doesn't need cryogenics to work. But there is a bit of power being amplified as well. So these devices, the fact that they're made as well of established technologies, neodymium crystals, are actually mass produced and exist. Have existed since the 1970s, and they are very, very useful potentially for quantum technologies, again being repurposed for a new type of optics communication. So if I turn it off, you can actually see then the system has a bit of delay. You can see the power begin to then diminish after a few cycles. So there's a bit of a delay, and yeah, you can see it basically going down to not background noise, because there is still the entangled source is still switched on, so there should be still a few more light gathering photons left in the system, even though it is passing through quite a lot of fiber, polarization maintaining fiber. There is polarization mode dispersion in the fiber itself, which is a big problem, which is actually why polarization entanglement is interesting, but it is problematic because of the optics, the specialized optics that's needed, in particular the fiber optics. So spatial light modulation and the manipulation of OAM states, orbital angular momentum states, are being examined as potential workarounds of this, and polarization entanglement itself may actually die maybe a quiet, silent death as a result. But nevertheless, you can actually do a lot of experiments with polarization, controlling, maintaining, and detecting apparatus using, again, bespoke technology, particularly stuff provided by this company, Tor Labs. So we can switch it on again, and then we can see the power increase back to its amplified state. So there we go. Yeah. So this setup is quite nice, that we can actually see the signal being amplified, and this is a polarization signal. that's originally generated from this nonlinear crystal here in the near infrared, fed through a fiber, and actually going through a crystal, a neodymium YAG crystal, which is pumped with a xenon flash lamp source, and the entangled photons are, if you like, riding on the echo, the photon echo that's produced from this pump, then detected, passed through fiber optics, split actually as well into horizontal and vertical states, and then detected with twin polar emitters. So when this setup is actually run, you can actually generate the data. You can get both the intensity, light intensity, the power, and actually the Stokes matrices, Stokes vectors, I should say, allowing one to reconstruct a density matrix of the shared mutually information, and actually look for entanglement measures, or plot the system as it evolves over time. Okay, so thanks very much for listening, and hope to share some more quantum entanglement and in general optics experiments with you all in the near future. So thank you.